I am Ramnath, who would like to share with you some information on the VLSI design topic, probability density and its impact on design yield. This is part 5. Other parts you can find it on the net. Please feel free to provide your comments or any suggestions. Thank you. Have a good day. Even though we want first time right silicon, it is not that easy. The process involved is bit more complicated because, as you know, there are several uh, processes involved in it. So the once the design is made, it is sent to fabrication, and that one will be tested. So during the testing, what happens is like the different types of wafers, that means like some wafers which are in fast corner, fast corner, typical corner, all these things will be tested in this specific scenario. Fast corner, where the drain source current of NMOS is high, and its probability distribution is shown here. In the same way, drain to source current of PMOS is shown here, and this is the probability distribution of that. So here, if you observe, this is the high value of current in both cases. That is the representation of fast corner. So in the same way, if you observe, the corresponding wafer will be assumed it is in this way. So there will be some dies will be taken from this fast corner, and silicon validation and testing is done as part of it. In the same way, slow corner. So here, drain source current of NMOS, drain source current of PMOS are very low. Okay, and in the same way, this is for the PMOS typical corner. So this one, and if you see here, this is the typical value, this is the corresponding wafer. Like that, different conditions of the wafers will be obtained. This is well described in part 4. So if you observe, different wafers are obtained. From these wafers, if you observe here, fast, slow. So NMOS is fast, PMOS is slow. Here, that is fast, slow. So different wafers are obtained. These wafers, for some of the dies from these wafers, are taken through silicon validation and testing. So what happens is, like, then we will know like how the first version of the silicon implementation in the fab is working. We will get to know. Based on that, further tunings are done in the next steps of the design, either through if it is small corrections need to be done through ECO, or through few layers of metal change, or through full all layers mask change. Okay, so to get to know about how these wafers behave, the models of these will be created, and that is called a process block, and that based on that process block, the devices will have slightly different characteristics based upon their performance, and based on that, the corresponding design views of the say, since we are talking about the digital design, the standard cells are created. So those standard cell views are used actually in the design implementation. So now the design is tested and implemented using different PVT corners, say SS corner, fast corner, typical corner, in some cases these corners. And then thus what is done is, like, the situations of the matrix lot kind of scenarios will be ensured to work successful. That is the main advantage of taking the design implementation through multiple PVT corners. So that is the main advantage. So once the design is tested, it will be taken once satisfied to work as per the data sheet, then it is sent for volume production. Let us consider the typical MOS design distribution of a NMOS. Here we are considering the drain to source current. There can be other design parameters such as VTH and other IDL and those things. So here we are considering only their probability distribution, and as you know, this is the typical nominal value, and this is done at voltage and temperature or at the nominal values. However, voltage and temperatures also can be at different values. That means like voltage can be 10% more or 10% less, and temperature can be very high, say 125 degrees or 150 degrees, or at -40 or 0 also. So based on that, these distribution curves will change, obviously. So this is one representation of this is the representation of several wafers and several lots actually. So this is actually in the fab, they also monitor these things, and this is the drain source current. Over a period of time they will monitor. So and they want to ensure that this distribution will not cross the upper specification limit and lower specification limit. So that is what, and in the previous parts we have covered this in detail, and this will represent the process capability index. So coming to the next part of it, so by considering different corners for drain to source current of NMOS, drain to source current of PMOS for different PVT conditions, we will be creating the, based on the process conditions, we will be creating different device models. Based on that, we will take it through the design implementation, and we will take it through the validation and testing. So when we are the fab, when they take it through some ring oscillators and some specific process metric transistors and all, when they double check it, they will find out that as part of the design also they do. So when they do the double checking, they will figure out that in the earlier 140 nanometer or 250 nanometer, those kind of earlier process geometries, they figured out that there is a slight difference between what the design implementation with the models they have used and with respect to the silicon. So they used later on some fudge factors. These are called uncertainty margins, and you can call it as small tweaking parameters. They say this is why they are doing is like, there will be a slight difference based on wafer to wafer difference and chip to chip difference now. So those parameters they call it as on chip variation. So those derates, small deviations, so they are added as part of the simulation, and they used to cover it and ensure that the silicon will be performing better or same as they thought in simulations. So in the later small geometry nodes, these OCV derates, on-chip variation derates, became slightly more cumbersome, and they added more, resulted in more area and power. So what they have done is like, instead of using those based on the performance corners, FF and SS and TT corners, and then using the OCVD rates, they wanted to use the slow global corners, fast global corners, and typical global corner, and then use other fudge factors, so that when they use the global corners, the distribution will be symmetrical. Here the distribution will be symmetrical, and hence they will be getting the best situation out of the simulations. So they started coming out with the flow global corners, and when they initially first started with the advanced on-chip variation delays. So, that one basically addressed only the delay and transition only of the standard cell logic. Later on, the Liberty variation format (LVF) or Synopsys (POCV) and Cadence (SOCV) formats also came in, and all of these three and AOCV used only the global corners. So when here if you observe that these global corners are used during STA time, slow global corner is used, and here in the hold fixing, both FFG and SSG are used. Okay, and the one point what we need to know is the standard deviation corresponding to this distribution and this distribution are different, and these two different distributions are further way lesser than the global distribution standard deviation. This is the global distribution, and the corresponding deviation sigma 1 sigma value is this much, but if you look at this distribution, the 1 sigma value is way smaller, so that is represented. So we need to know that by using all these global corners and sigma values, we need to come out with the we need to use the appropriate device models and implement the design. Let us analyze a little bit more on the probability distribution and the different parameters associated with it. So as we know, this is the probability density function. Here mu is the mean, sigma is the standard deviation, x is the design parameter. We can consider this as drain source current or linear current or the VTH value, like that. So if we plot this distribution, it will be fx will be in this way, x will be in this way. So here this is the mean, so mean to sigma, and this value on the other hand. So if you take this, this is the general curve, and if you take this to be Gaussian distribution, then the values will be 34.13% from 1 sigma, and this way it is 34.13. Coming back, so since we need to fix the hold to ensure that chip will function as expected, so we need to know that the most of the hold fixes are needed only in the FFG column. Okay, here. Okay, so in this situation, the design parameter we are considering is the not the same value as the drain source current. Here we are considering the delay of a cell. So in the fast corner, the delay will be smaller. Here is the slow global corner, so the delay will be more. This is the mean value. So if the when we are trying to fix the hold values, then we will observe that the most of the hold fixes are needed in the fast global corner. It doesn't mean that in the slow global corner and typical global corner the hold fixes are not needed. That is not the correct statement. Hold need to be fixed in all corners. And this distribution, this is the local distribution. So if you observe, it will be in this way. Okay, colors need not be same. Okay, because of cut and paste I did, it came out to be same. So if you observe within this small distribution, again we have the standard deviation we have, and that sigma L will be different. So now let us analyze a bit on how these sigma and mu are related. So from 1 sigma, if you observe 1 sigma, 2 sigma and 3 sigma, if you observe that the points are the 34.13% away from the mean mu, and the minus 2 sigma to 1 sigma, the number of points are 13.59 here, 1 sigma to 2 sigma. Mu to 1 sigma is 34.13, and here it is between minus 3 sigma to 2 sigma. That means like minus 3 sigma to minus 2 sigma, the number of points are only 2.14% here. So small, so little values are actually will be existing within this much. And if you observe how many points are after 3 sigma, minus 3 sigma are just this much. That means like very less, 0.13% only. So you can always say that in 100 only 0.13 values. So that means like it is very less. But where it makes a difference is when you are computing in terms of millions of chips or billions of chips. That is when all these things come into play. That means like, as I mentioned earlier, like when a car is being rolled out from one manufacturing unit, say 1,000 cars are manufactured at single time, and you have some around 600 to 2,000 chips exist in a car, and if you want to figure out how many you will be manufacturing in a month, if you consider all that, then the numbers will blow up. Okay, so if you consider these things, and one more point what I want to mention is this FFG and FF corners are very close. That means like the FFG corner will be as close as 2.7 sigma or 2.8 sigma away from the mean. FF corner, the performance corner, will be 3 sigma away from the mean. FFG corner will be 2.7 or 2.8 sigma away. That means like this difference is very less, because global standard deviation is far greater than local standard deviation. Here this is the local standard deviation. So when we are performing the hold, we need to ensure that it needs to be done with respect to FFG and SSG. Yeah. Let us investigate further on the global corner of typical, fast, and slow global corners and the associated VT variations. Okay, so if you observe here, the typical global corner, nominal voltage and typical temperature, usually it is 25 degrees C, and this nominal voltage changes with respect to the geometric node. Why it changes? Because of scaling. Okay, we want to ensure that gate oxides won't break down. The nominal voltage at 140 nanometer is close to 1.6 voltage or 1.8 volts, and in the case of 60 nanometer and all, the nominal voltage will come down drastically. And so if you observe, so in a particular hold slack, typical one, the probability distribution will be somewhat, say, in this fashion. Okay, definitely these negative slack values need to be fixed. Okay, so this is just one typical distribution. So when you perform for the same design at the FFG corner, nominal voltage plus 10% voltage and high temperature, sometimes we need to perform at multiple corners, as I mentioned, fast global corner, nominal plus 10% and minus 40 degrees centigrade or minus 20 degrees centigrade, like that. The distributions will be different. So here if you observe, there are more timing paths which are having negative slack. Okay, assume that this is the 0th value, these are the negative values, these are the positive values. Then most of them are at the negative values. And if you observe here, the slow global corner, nominal minus 10% voltage, low temperature. If you observe, it can also be high temperature. Okay, the distribution will be different. So here, if you observe in a typical scenario, there will be more positive scenarios. Okay, but don't think that this is the kind of like a given and golden statement. Okay, there can be, and one more thing is these distribution are not drawn to scale. So if you observe, actually there can be certain situations wherein in a design the FFG nominal plus 10% and high temperature can be in this fashion, and the others can be in this way. And in some other situations, the slow global corner can have negative values. That is true. It is, in the coming slides we will be able to show you more. So it is not necessary that always the slow global corner nominal minus 10% and low temperature will have always the positive slack, whole slack. So far we have understood how the MOS device transistor, if it is an NMOS or a PMOS or of a different VT, how their process distribution, how their different corners, like typical corner, flow, fast global corner, like the different PVT corners and VT, how they will change and all. The defects parts per million. However, if you apply the MOS transistors, because in the timing path there will be many transistors existing, and cumulatively how they will play a role. So if you want to see that one, then let us consider one timing path. In this timing path, in this scenario, there are different instances of different VTs and different drive strengths. So this is the last common instance of the timing path, and this is part of the launch clock path. This is part of the capture clock path, and this is part of the data path element, and this is the launch clock path register, and this is the capture flop. So the data will move from here, clock to queue, and then reach here, and then if in the other way it will also reach up to this point, then the hold value we will ensure whether it is met or not. So if we there are now different transistors exist in this whole timing path, and their functionalities are also different. So considering all that, in this specific timing path, so assume that the typical corner where hold slack is say 10 nanosecond. Then what we will understand is, say in this whole different wafers and different lots and other things, assume the it is having 10 nanosecond and the distribution is in this fashion. Okay, and in the fast corner or fast global corner, the value is say 4 nanosecond, and in the slow or slow global corner, say it is 14 nanosecond. So if it is slow global corner, it will shift somewhere here. In the fast global corner, somewhere here. Okay, so grossly we can think that this is generally a normal distribution, Gaussian distribution. That means like the shift is symmetrical. But in the normal scenario, these instances will be of different in nature, and also the VT, voltage and temperature, will be different. So these values what you will be getting here is different, as we have shown in the earlier slide. So what we need to remember is, like, this is a one typical scenario, and this is not the only possibility to be understood and fixed. So if we actually figure out in soft design, there are multiple of these variations. That means like one will have more drive strength, and in another timing path this will have smaller drive strength, and this will have a different VT. Like that, different possibilities exist. So if you observe all that, then we need to remember that the design which is closed at typical corner, considering the 3 sigma variations, you will observe that the actual DPMO observed is actually 2700 parts per million. However, this is not the true thing. If it happens, definitely this is a non-profitable wafers we are preparing. However, actually how it will be is like we will tweak the design. That means like we will ensure that the design is meeting in the fast corner when we are working with the OCVD rates, or fast global corner when we are working with the OCVD rates, or LVF format. So we will ensure those conditions and then fix this last part. By doing so, what we are ensuring is like these are the probability of failure items. So that means like from this onwards, that means like not 4 nanosecond, I am saying. So in the fast corner, if you see, that means like here design is met comfortably, hence we are seeing 4 nanosecond, but otherwise assume that this is at 0 nanosecond fast corner. Then you will see that this situation more than if we move towards this, there will be a fail in the hold slack. So if that happens, then those parts need to be eliminated before going to the customer. So if you see that one, to prevent lesser of these items to fail, what we are doing is we are fixing the design at this point, not at this point, and applying the 3 sigma and ensuring that the whole design will work. No, we are not doing that. And in the same way, slow corner. Why we don't fix in this specific case at the slow corner is hold slack is already met. Okay, we will now show some other scenarios, and then when the whole soft design scenario, and then show why we need to fix even in the slow corner. Okay, so in a normal soft design environment, the these elements will be at different configurations. So since they are different, so the ultimately even if we take PVT3 as slow corner, there will be some timing paths which will be slightly failing. Okay, as I showed earlier, this is one typical scenario. Sometimes the overlap may be on this side, that you will see that there are some failures here even in the PVT3. So assume that this is fast corner, then there are more failures in the fast corner. So like that, because there are so many different timing paths which will have different instances of this one. So we need to ensure that all of these in different PVT corners, the timing path is fixed. That means like hold is more than 0 nanosecond. So even in this fast corner, all these minus 20 nanosecond and all of them need to be fixed. Even in this PVT3, there are some which are in here violating PVT3. Those also need to be fixed, and all of them need to be brought more than 0 nanosecond. And here what we also need to observe is like there are some timing paths in fast corner which are mutually exclusive to slow corner. So if we fix some of them, doesn't mean that we need to all these slow corner they need also we need to fix. It is not necessary. So if we fix in one of them, already the slow corner it is fixed already, and vice versa. So these are some items which we need to know when we are working with the composite fashion, when all the different transistors are working together. We will figure out in this slide how the probability distribution or the process implementation will play a role. Definitely the other processes such as testing will also play a role. Here we will restrict our analysis to these two parts. So as we have learned earlier, based on the MOS transistor, we figured out that how the process capability index when it is now 1.33 or for 1.66 and 2.0, how that will affect the yield. That means like how closely the design parameter varies within the specification limits. Based on that, the standard deviation depends on the in the case of the process side, and that will have direct impact on the yield. Okay. However, since the other process, the design implementation is a sequential one which follows the fabrication. That means like you can consider that after implementation comes the fabrication. So these two together impact the overall or effective yield. So this is the usual process wise how the yield differs, and the process is tweaked at the typical corner, which will result in fast corner and slow corner. And these performance corners are 3 sigma away. So when it is plus or minus 1 sigma, the number of pass situations, this is the sigma global variation, is 68%. That means like 34% here, 34% within 1 sigma. So 68% points exist in this. So these are all pass points. So when we are considering plus or minus 1 sigma, whatever is outside this plus 1 sigma, outside the minus 1 sigma are fail points. So 100 minus 68 means close to 31%. So out of 100 points, 31 are defects. So if you consider a million opportunities, there are these many defects exist. So this is the manufacturing process. So if you consider plus or minus 3 sigma, then the number of defect opportunities are these many. So we need to ensure that in this process DPMO between plus or minus 3 sigma of typical corner is 2700, and these are all random in nature. Okay, so these are all from fast corner to slow corner. Now coming to the design implementation, as I have mentioned, in the lower geometric nodes and all, we will perform it at the global corner. So in the global corner here, so this is the performance corner for the simplicity, showing only one scenario. So this is the local variation of the standard deviation. In the same way, all these exist. So these are all tweaked to ensure that the design is implemented correctly. Okay, so we need to know that if we want the sigma to be high, design yield to be high, then both in the process fabrication and the design implementation, silicon testing, all those places we need to ensure that the design yield should be proper. Actually, in these two places it makes a big difference. In the silicon testing, we will observe something, and further we will use that information in tuning the implementation in the next phase. Okay, we can also tune the process of the fabrication to get more yield. That is a bit more complicated. So to understand now to get the effective DPMO, whatever happens in the manufacturing process, whatever happens in the implementation, these two play a role, and together we will get the effective DPMO. In the case of critical auto products, what we need to ensure is the plus or minus 6 sigma we need to go, so that the effective the DPMO is close to 2 parts per billion. Okay, and in the same way, design implementation phase also, we need to go and close the design up to 6 sigma. Then only we will get DPMO of 2 parts per billion. So effectively, both in the case of process and manufacturing implementation, we will get the effective DPMO in the order of 1 parts per billion. Okay, so that is how the yield and the probability distributions of a transistor, of a timing path, the probability distribution in a process, the process capability index, and the design implementation, all these things, how the AOCVD rates, LVF, all these things will play a role. Please go through these references at your convenience to improve the understanding and to get more details on the concepts presented. Okay, have a good day and enjoy. Bye.